Hello, hello. Today we are gonna continue onwards in terms of doing some more physics-based stuff. Um, let's see, changes. We also need to, let's see, not checklist. Change the way that the bounding volumes get recalculated. Look into the way the object transform handles interacts rather with bounding volumes. Yeah, we need to fix that. Right now, our debug helpers are set simulations. We have some. We do have a start of some collision detection. Let's see, rendering features. Game mechanics. Yeah, we're not getting there yet. At least we do not. Modeling different models. Weapon model. All right, a HUD. Let's add this as a question mark. I'm not sure whether we need that. Yeah, I never got to create a Discord channel. We also need the bug fixes. Okay, I think that is what we need to update in terms of the whole roadmap. Let me see. Let me see. All right, I noticed a bug in our last episode, which was the separating velocity is fine, but this has to be um, a negative separating velocity if the as you can see here, the change in velocity depends on um, the dot product between the contact normal and the actual velocity, meaning if they are parallel, we'll get a 1. If they are pointing in opposite direction, which they might, which could mean that that the objects are moving towards each other. This checks if they are not, it's not below 0, we're not moving towards each other. We're actually resolving a previous, perhaps, collision or something else. But anyway, the new separating velocity is by taking this scalar, which is going to be more negative whenever a lot of the velocity is projected on the contact normal. We do take a positive version of that, meaning that if it is projected highly for instance, like a total of 1, we use a lot of the restitution factor, which is the factor on how bouncy the whole collision is expected to be, and how much change in velocity is needed in the direction of the contact normal, which is away from the object which we collide with. Yeah, and this is going to be a usually positive number, or perhaps close to 0, but anyway, this is going to be a positive number because of this clause here, uh, meaning that when we subtract the negative number, we get an even higher change of velocity, meaning that even if this is 0, there's no restitution, we do project some separating velocity, and we calculate the impulse by taking the inverse mass and dividing it into the expected magnitude of the velocity, and we take the contact normal and multiply it by the magnitude, which is the final impulse. So meaning that if we have no restitution, we still get a separating velocity by projecting the initial velocity along the contact normal. The more they are directly opposite, or rather, yeah, actually, the more they are opposite, meaning that the object is heading towards the static object, which we're checking for this collision with, the more separating velocity the impulse will have. And if it's more bouncy, the interaction itself, we will have even more outgoing velocity. We calculate the final impulse and update the velocity by adding the old velocity with the new velocity impulse, which we scale up again in terms of the mass. So the velocity is relative to the mass. Yeah, so we end up with a system where we do get a bit of bounciness. I'll show you later what the amount I said was. I set the bounciness to 0.30. We could set it even lower. And if the sign of the new separating velocity wasn't correct, we would get some opposite behavior. And as you can see here, if I zoom out, we actually have a collision with the floor and the wall. There's a minor bug here where we only when we kind of get unstuck in the floor, the collisions actually update, meaning that, as you can see here, it stays in a state where we indicate a collision, and that's because we have added the separating velocity, which when the objects are moving towards each other gets calculated, and a bit of bounciness gets added Even though there are no bounciness, for instance, that we should indicate that during this collision, the objects will kind of stick to each other. As you can see here, we do not get pushed out. We just kind of stick. There's actually some interpenetration here, which we need to resolve afterwards, which will be some basic repositioning, which will be what we will do for now. We will do the iterative solver whenever we add more objects, which could be a interesting way to try to go today. We might want to perhaps create another object where we can have dynamic interactions. So we can have checks for the dynamic objects themselves, and then checks between the, or rather between the all the dynamic objects, and then checks between the the dynamic objects. And yeah, we would definitely need a iterative solver algorithm for that. But yeah, we will look into it later on. Let's see. So let's see. So we do get some distances out of our collisions. So let's see. Do we? Yeah, we do it inside the resolution. So we calculate the distance. Let's see. This is supposed to be alongside the contact normal. Maybe we want to do calculations of we want to calculate the actual penetration here. And we query for the closest point to the center, and we normalize it and treat it as a contact normal. Let's see. We could multiply that contact normal and compare it to the path width. The problem is the contact normal might be We could do maybe SIMD apps. Yeah. Yeah, so we could do that. As a way, because right now we calculate the total distance between the center of the object and the closest point on the object which we are colliding with. But for us to calculate the penetration depth, we have to kind of know how big our bounding volume is and how far from the center we are um, kind of uh, extending down through the contact normal. Um, we could do uh, maybe just hmm, yeah, so I was just wondering whether I should do an absolute method on uh, yeah, we could do that. Then I don't have to speculate whether the contact normal is positive or negative. Then I'll always have whatever I need. And I can use since the contact normal, at least for these straight boxes, uh, will have two axes that are 0, 0, and then it will have the direction of the contact normal, which for our current solution only can be along the y, along the x, or along the z axis. Yeah, so that could be a way of doing it. Let's see. Let me just dump the distances at least. Distances. Let's just print them. Distance. There we go. Let's just do that for every collision. Oh well. Oh, well, I haven't filled anything into the vector. So we of course do it like that. So 3, as you can see here. And let's just do some checking here. Well, that's not it. There we go. We want the dynamic bounding volumes. We want the dynamic bounding volumes. And we want the half widths. Let's do X and then do the same for EY. And then the C. And we of course have to adjust this. So since it's a positive number, I suspect that we are interpenetrating. Yeah, it definitely gets higher or lower whenever I kind of go out of. And here we do get. Okay, let's see. So if we try to do some calculations here, instead of that we do in I less than distances dot size, and then there we go. And we can actually calculate a vector multiplied by scalar, and we take our contact normals and we take our distances I, and we kind of dump the test vec here, x test vec y c. Let's see the test vector. So yeah, let me just or rather, let's just disable that as to not get too much clutter in here. So and as you can see, let's see. All right, we fell out of the screen, I think. Or did we? No, we ended up here. Yeah. So it actually gives an X and C. And down here, it gives us what? Let me see, I flew out of the map. Let me just test what values we get down here. 0. Well, we do have a problem then by using the contact normal. Let's see. What result do we actually get down here? Yeah. Seems like the lowest value here is okay, let's disable the test vector. So these two are negative. These can be positive. I think we are mostly having a collision on the x-axis here. Let's see. As well as here. This is going to be the C. This is, oh. But, I mean, where are we? Are we? And we are stuck. This is a hovercraft game. Physics are a lot of fun, but you can definitely not handle everything. So if I get on the other side of this, let's just keep it that way. I mean, yeah, we suddenly change signs. Ah. So the problem is, should we compare? Maybe we don't want to do that. Maybe we just want to take the dynamic object and test it if distances I is maybe lower than this. X is lower. Then width And if we do the same for the y, let's just do some testing here. Or rather, else if. Y is lower than width. C is lower than width. Dist on. Yeah, that's more clear because dist on Y is lower than width. All right. So yeah, X is lower than width. So that is also, as predicted, X is lower than width. X is lower than width. Yeah. Y is lower than width. Well, I don't agree on that. Let's see. Where did we go? Where did we go? Where did we go? Okay. Should implement a reset button of sorts. So, yeah. Yeah, so right here, it kind of lets me know that the y-axis. Well, that's because, no, that's not because. Let's try to fly this shuttle over here. Oh my god. So, we have a problem here where I can't tell if, let's see. Let's lift this bad boy up here. The controls are inverted because I flipped the camera. I'm sorry that you have to witness all of this. Let's see. So, yeah, we're gonna lift it up, over. Of course, I need to see the console here. So, yeah, it still thinks the Y distance is lower than whatever point. Has this something to do with the way we transform the negative C? Let's see. Let's try this. Instead, no, then the bounding volume doesn't get calculated correctly. All right. What if we do 3.15? Let's try that. Just simply flip it around the y-axis. It still says that dy is which is kind of weird to me. Anyway, so to get the, let's just Google it, penetration. Well, collision bounding box. Uh, the contact. So mm, uh, um, let me just look up. Let me just see. Mm. Uh, well. Well. Let me just see. Yeah, no. I'm looking through some different stuff about querying. Closest point, we already have that. Distance of point. Maybe if we kind of flip this around. Um, Maybe we want to check the closest point here, and then between the A list. Let's try that instead. Let's try that instead. See if that actually gives us any useful information. Let's use this. Distance is 0. No, that doesn't work. At least not the way I did it. So we could also just well, isn't that what we already did? If we kind of subtract if we have a penetration, we get the closest point to the center on the object where we are. So let's try to draw it here. Uh, or rather like this. So if we have a point here, we have a bounding volume of sorts. And we find the point here that is closest on this volume here to the center. We could do the distance between this point. Let's see, what did we do before? We did from the center. Let's see. Uh, okay. So yeah, this basically skips the whole thing up here, which means that if we feed that result into the algorithm, we actually get a 0. Yeah, so this is so yeah, if we revert back to that, but the contact normal still does tell us which way the penetration is going to be resolved. Let's see. So let's do this again. Test vec is going to multiply the contact normal by not a scalar. Let's see, maybe we can do the vector dot product math dot product and the No, that doesn't make any sense. That doesn't make any sense. So, multiply, vector multiply. Test vec x. Test vec y. C. Let's see. Let's do, remove this. And let's do one with a new line here. So yeah, right now this signifies the so yeah, this tells us that the y component is active, the x component is active, both the x and y, rather the c component is active down here, and of course whenever we collide with another point up here, we both get yeah, so the C component is active. Yeah, so if we use the contact normal, we can, if we just start with whatever I thought of doing, eventually you could see the contact normal. It should be normalized. We multiply. Yeah. Maybe if we do something like scales normal, let's try that. Math, scalar, contact normals, and the distance. And let's do the scaled normal here. This, of course, doesn't make any sense. Let's see. Math subtract. let's see. So the x-axis is the lowest one. The x-axis is still the lowest one. And the y-axis here is the lowest one. The x-axis is suddenly the lowest one. The c-axis is now the lowest one here. Well, yeah, now from that side the C is the lowest one. Here, yeah. I think I'm gonna add a math function here. Which we will use to let's see, let's do inline g vector. Let's see, a vector call. And we want to return and we want to there we go. Let's do an inline g vector vector apps, and we take a gc vector reference vector, and we return the and on and the vector. So yeah, we do that. Apps. There we go. Now the c-axis is the lowest one as expected. Yeah, well, you end up by subtracting. Let's just, instead of doing this, we will use this and ask it to multiply the absoluted version with the bounding box half widths, and then we will get whatever. And maybe we even do math here, scalar, and then add in the distance, or rather multiply by the distances. Let's see, not here exactly, maybe multiply scalar. This is going to return a vector. Distances. There we go. Let's try that instead. That looks more right. So maybe we don't want to do that actually. Or rather, let's see, maybe we want to mm, 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 mm. Hmm. So the problem is that I'm not very good at this. But besides that, I want to find the axis where the penetration is. I sort of get it by absoluting the contact normal. Then we want to check if the half width over that contact normal. So we can use this as a way of saying I want to take the absolute of the contact normal and multiply that by the half widths. Whatever is left is our defining axis. This needs to be, well, yeah. If it's negative when we subtract the distance, Also, if we do test vec2, we do the same thing here. And instead of this, we do scalar. And we do the distances. And then we solve, we subtract. We subtract the test vec by this, and then we ask for the result instead. Let's see. Yeah, so now we have the penetration depth on the y-axis. As you can see, it gets slower whenever we start to float. And whenever we move out of the object, let's see, does it work from the other side? Seems like it. So this actually works, it seems. Uh, yeah, the C here. What happens if we get up here? Yeah, there's also some penetration on Y. Yeah, whenever the sensor goes over the contact normal changes, we just have to be mindful of that. Yeah, maybe we can use this result as a way to I would though like to get a different algorithm here. Yeah, I would prefer to get it in another way. We could also do something like perhaps could we do something simple like, I mean, so if we for instance use this wall here, RC, so yeah, here it says that the Y is the one colliding and the C is getting negative. There we got all three. I don't think this method is robust. enough. So what did this dude suggest? Which to travel? Yeah. Yeah. All right. So that's a way of doing it. Man. Let's see. So we yeah, we have to. And we have to do more complicated math to kind of do it all with rotations. And if we just dump the distance here. Yeah, we've been playing around with this for a while. I think we should just so if we just do a simple man's algorithm, let's see, we want to do something like calculate axis and penetration depth, and we take in the bounding box, we take in the distance, okay, so we want to check the distance is gonna be lower than, for example, the y half width, which means we're interpenetrating if it's larger than the y half width, for instance. Yeah, I think we will do it like that. Let's decide on our out values later. The half width x size is if the x distance well minus the distance is larger than 0, and then return. Let's do a g vector out axis and let's do a float depth reference. So we out depth, we pass this out of our function here. Let's try that. So the g vector, or rather this gets stored outside. The out axis is equal to 1, 0, 0, 0, and the out depth, flow depth equal to 0, 0, 0. And let's just say the out depth is equal to depth. Let's try this. And let's just set the axis here as 0, 0, 0, 0, and the out depth will be set to 0. I know we will reset it, but just to do some error checking here. Let's try that. Physics. Calculate penetration depth. There we go. The distance I, and we want to store g vector result. Pass in the result. Load pen depth equal to 0. And let's see. Let's do result axis. And do a depth, pen depth. Let's try that. Yeah, meaning that we do it on the Y, we do it on the C, even though, yeah, then we end up doing it on the Y. Yeah, that's the way the yeah, we definitely do not have support for um, something like that. Yeah, we need a more robust collision checking algorithm, or maybe a more robust query. I mean, so yeah, you could argue that it's not totally imprecise. So this is, it really does think that the Y is the right one here. I mean, yeah. Is the axis actually not needed? Let's see. Maybe we just want to calculate the penetration depth. I mean, it does get reduced whenever we move the object backwards. And I mean, could this correspond to a penetration depth of that much? Oh well, whenever I rotate the whole thing, the coordinate system seems to be messing with me. I mean, does this? It actually changes how the oh yeah, it's because I do not. Yeah, it's still working as intended. I'm just getting confused whenever the camera rotates, the controls doesn't, because the character doesn't rotate. So yeah. Anyway, maybe the penetration depth is actually correct anyway. Maybe we do not want a axis being outputted. Let's try resetting that. Oh, rather, not that. There we go. Yeah, we simply do some penetration gymnastics here. No giggities, please. Yeah, this will work for now until we get a more robust collision detection system. Okay. Let's see. We could do. We could combine this since we don't need the distance. Yeah. This is not very robust. As you can see, there are edge cases where this won't work. Right now, we won't support going up on walls. I think even if we walked on stairs, we would like to. Yeah. Yeah. Yeah, there's definitely some quirks to this solution. Yeah, we definitely need something more robust. And maybe we should do this as an internal version instead. Maybe just some. Let's see. Calculate penetration depth. Maybe we just want to return the thing instead. Rename this. Remove this. Instead of doing like that, we simply return depth. Delete that. Otherwise, we return depth. Let's try that. And instead of and depth, pen depth. Nah, let's. Maybe we don't want to store the distances. Calculate contact normal. Maybe we don't want to. mess with that. Maybe we don't want to do the same thing here since they don't overlap at all. We want to do the contact normal. We don't want the distances. There we go. We don't want this anymore. Let's just delete it. Then we want some load penetration depths, and we want a system where we wrap that. This is going to be an internal function. This is going to be calculate penetration depth, and we do this, and we do collider collided. Let's just call it that, and then we pass in a vector of floats, penetration depth. And then we do a float called distance, which is equal to the query squared distance. Yeah, instead of doing the square root, we could do the collider center and the collided. There we go. We get the squared. Squared. Nah. We just do this square root here. And then we ask the system let's just move this up because we want to do it like that. And then we ask the system, please calculate the penetration depth of our collider here and with the specific distance. And we add that to the vector here. Let's see, physics. And we take same values here. The collided. And then the penetration depths. And store that. Then just test this. We print pen depth. Which looks pretty good. Yeah, next we want to do some repositioning. So we want a method here that is called resolve collision penetration. And we want the same information here, except we want the float of the depth, pen depth. And we want to resolve this penetration here. Let's see. So if the pen depth is less than or equal to 0, we simply just return. We do not need to do anything. Then we do a vector movement, which is the contact normal multiply the contact normal by scalar, math scalar, vec multiply scalar. So the contact normal needs to be multiplied by the pen depth time, or rather by the divided by the object's inverse mass. Since the movement in general is dependent on let's do a movement scaled by mass, and then then we update the then we set the movement vector, and we multiply that. Yeah, maybe we don't need this right now. Yeah, maybe we don't need this. Multiply scalar, let's do contact normal and the pen depth. And we do update the physics object position is equal to the two vectors added, add and the movement. And actually, I think that is it. Let's try that. So instead of calling that method, we call the physics object, the contact normal, and instead we do the penetration depth for this specific penetration. Yeah, now we don't sink into the actual object, which looks really nice. It looks kind of awkward. Okay, something is somewhat odd with that movement depth right there. Yeah, the repositioning is too much on that axis. I mean, it works on the flat size. I think it's our penetration depth calculation that is not working properly. So yeah, that works. Yeah, we could definitely do some adjustments. Yeah, some of this is somewhat error prone. I think it's the way we calculate the penetration depth that is the problem. Let's do a let's do something somewhat different here. We want to find the lowest float. Let's see, float max. And we don't want to. Let's do a temporary here. Min depth temporary, which is like that. We set the temporary like that. If the minimum depth is higher than the temp, we set the minimum depth to the temp. And instead of doing that, we do like this, and we do the same checking for every piece of the algorithm. So we find the uh, lowest distance here. Let's see what happened. Something definitely didn't work. uh, All right. That definitely didn't work as intended. If the temp is lower, or rather, yeah, we check that the temp is actually more than 0 here. Otherwise, we can't end up like that. Let's just do. Oh, we return, of course, yeah. Well, that doesn't matter much, does it? Yeah, let's see. Yeah, the penetration depth. It's really low. I mean, this is also somewhat low. Low. This is also low. Let's see. And this means all right. So this is sometimes equal to the float max. So yeah, if the minimum depth is unlike the maximum value of a float, we return the minimum depth. Otherwise, we just return 0. There we go. And this should work. There we go. Let's see. So we do not get the ugly bouncing, but we do not get a completely nice bounding volume. Uh, Distancing on that plane. It works way better on the other planes. I mean, even if we test this, let's try to save this. Yeah, I'll just reset. I ended up adding way too much force here. Let's see. I mean, Yeah, it really just rests upon the floor now as compared to this, I think. Well, it's really close. Anyway, doesn't make much of a difference. Let's see here. Here you can see, well, no, it doesn't really do a lot of a difference here. On that plane, everything works as intended. Let's see, whenever we go really deep here, yeah, most of the arm actually gets cut off. Yeah, almost into the hand, the whole of the hand. Let's just see, does this do any difference? It does add a bit more, it seems, but it's not much. Without this added, does the penetration depth get higher? Yeah, it does something at least. It seems like it corrects the penetration depth somewhat. Um, somewhat. We could try just another version where we do. I'm not sure this is going to be. There we go, and then we calculate the final movement, which is going to be the multiplication of this by the inverse mass. Let's see, does that do anything different? Oh, did I not enable it? No, I didn't. Yeah, the penetration depth really does get small, very small, at least from the calculator's perspective. And let's see, do we agree? So if I do like this and just push it into the wall and compare it to when I push it into the wall like this, yeah, we definitely need to rework some parts of this system. Yeah, it does look a bit deeper. Yeah, I'm not calculating the penetration depths correctly, I think. Yeah, I'm guessing that's the problem. Um, yeah, I'm guessing that's the problem. We could then change it. To ask it the yeah, we could do a situation where we tell it the contact normal instead. Uh, mm, we could do that instead. Would we rather do that? Filter out the contact normal and just do whatever subtraction needed. Yeah, we need something that is way more robust. I mean, only comparing boxes to boxes is yeah, well, is it I guess it does sort of work. I guess it does sort of work. Yeah. Well, we definitely want something more elaborate in time. But yeah, for now it will work. Okay, I'm gonna have a break. Um, which means I'll cut the YouTube video here. Although it annoys me to leave everything in a place like this. Alright, we just do one tiny thing then that perhaps is somewhat more reliable. Yeah, we do it like so for the collision index. Uh, Yeah. Okay, let me just do oh well. Okay, I guess I'll do it. Well, it puts the contact normal into that. Yeah, we do like this instead. And we add the well, we actually pass in the contact normal. Wait a minute. Oh, that's the resolver. Wait a no, never mind. Collider collided. Ouch. And we do a GC vector reference contact normal. Uh, GC vector reference axis. So we redo this function here, and we redo this. Huh? Oh well, yeah, we also need the contact normal here. Right. Did I mess things up now? Did I mess things up in here? No. Oh well, just IntelliSense being slow then. All right, let's undo this code here. We want to check if the axis x is bigger than 0. The y, the c, then we return that, or that, or that, or we return 0, 0. Let's simply, let's see, where is the error in our application here. We do the contact normals, there we go. Okay. It does look better. Or it does it? Do we even have the... Yeah, we do have it on. Huh. It really annoys me. And our rotations down here aren't messed up, right? Let's see. Ah well, it doesn't really matter then. I'm either not calculating the right point. Uh, yeah, we could change this away from a vector. Yeah. Okay, I'm gonna have that break. Doesn't change anything, and I think I need to clear my mind a bit and get something to eat. Hopefully, you didn't regret tuning in on this episode. It didn't really do much for now. Uh, Later on, I will be continuing onwards in terms of deciding on what to do next. Yeah, hopefully I'll be